Axiom of Completeness and Existence of Square Roots. In this video, we discuss the most distinctive assumption about the real number system and use it to show that every non-negative real number has a square root. The defining difference between the real numbers and the rational numbers is that the set R of real numbers does not contain the gaps that permeate the set Q of rational numbers. The most precise way to phrase this assumption is perhaps as follows. Axiom of Completeness, which we shall in short call AOC. It is like this. Every non-empty subset of R that is bounded above has a least upper bound in R. An axiom in mathematics is an accepted assumption to be used without proof. Ideally, an axiom should be an elementary statement which is so fundamental that it seems to require no justification. To understand the meaning of axiom of completeness, we need the following definitions. A subset capital A of R is said to be bounded above if there exists a number u, small u, in R such that A is less than or equal to u for all A in capital A. Such a number u is called an upper bound for A. Second definition is a number small r in R is said to be the least upper bound for a subset capital A of R if it satisfies the following conditions. First one is R is an upper bound for A and R is less than or equal to every upper bound of A. R is less than or equal to u if u is an upper bound for A. A subset B of R is said to have a smallest element if there exists an element S in capital B such that S is less than or equal to every element of B. The element S, if exists, is unique and is called the smallest element of B. That means a set can have at the most one smallest element. It is not difficult to see that although a set can have a host of upper bounds, it can have only one least upper bound. The least upper bound for a set capital A is most popularly called the supremum of the set A and is denoted by sup A. The axiom of completeness says that if A is a non-empty subset of R such that there exists u in R satisfying A less than or equal to u for all A in A, then sup A also exists. That is, the set of all upper bounds of A has a smallest element. The set of all u in R such that A less than or equal to u for all A in A, this set has a smallest element. Some consequences of axiom of completeness. First one is Archimedean property. Given any real number x, there exists a natural number n such that n greater than x. And number 2, given any real number y, there exists a natural number n such that 1 upon n is less than y. The first part is equivalent to saying that n is not bounded above. And the second part follows from the first part by letting x equal to 1 upon y. So it is enough to show that n is not bounded above. And we do this using axiom of completeness. So let us assume for a contradiction that n is bounded above. Then by axiom of completeness, n has a least upper bound. We call it alpha. Clearly, by the definition of least upper bound, alpha minus 1 cannot be an upper bound for the set of natural numbers, because alpha is the supremum, least upper bound. So this alpha minus 1 cannot be a upper bound of n. Therefore, there exists a natural number n such that n is greater than alpha minus 1. But this is equivalent to saying that alpha is less than n plus 1. Since n plus 1 is also a natural number, we have a contradiction to the fact that alpha is an upper bound for n. And this contradiction shows that n cannot be bounded above. So this completes the proof. We now demonstrate how axiom of completeness helps us prove the following result. There exists a number alpha such that alpha square is equal to 2. That means 2 has a square root in R. Let us consider the set capital T equal to set of all real number t such that t square is less than 2. Clearly this set is bounded above. For example, 2 is an upper bound for t. If not, then there exists some t naught in capital T such that t naught is greater than 2. And so t naught square will be greater than 4, which is false because t naught is an element of t and therefore t naught square has to be less than 2. Therefore, by axiom of choice, t has a least upper bound in R. We call it alpha. We will show that alpha square equal to 2 by ruling out the possibilities alpha square less than 2 and alpha square greater than 2. Let us first assume that alpha square is less than 2. Note that for each natural number n we have alpha plus 1 upon n square is less than or equal to alpha square plus twice alpha plus 1 by n. This less than or equal to because n is greater than or equal to 1, so 1 upon n square is less than or equal to 1 upon n. The assumption alpha square less than 2 enables us to choose n large enough so that this quantity is less than 2. That means this particular quantity is less than 2. So in that case, this alpha plus 1 upon n square will be less than 2. Okay, so we have to choose small n so that this is less than 2. Specifically, we can choose n naught in n large enough so that n naught is greater than twice alpha plus 1 by 2 minus alpha square, and we can do this by Archimedean property. In that case, we have alpha square plus 2 alpha plus 1 by n naught less than 2. So if n naught is greater than this, you can see that alpha square plus 2 alpha plus 1 by n naught is less than 2. And so this quantity is less than 2. Thus, alpha plus 1 upon n naught is also an element of T, which contradicts the fact that alpha is an upper bound for T. Okay, because this element is bigger than alpha and still it is inside T. Therefore, we cannot have alpha square strictly less than 2. Next, let us assume that alpha square is greater than 2. Note that for all natural number n, we have alpha minus 1 upon n square is strictly greater than alpha square minus twice alpha by n. Okay. We then choose n1 in the set of natural numbers large enough so that n1 is bigger than twice alpha by alpha square minus 2. So we again do this using Archimedean property. So in that case, this quantity alpha square minus 2 alpha by n1 will be strictly greater than 2. So alpha square minus 2 alpha by n1 is strictly greater than 2. And so alpha minus 1 upon n square, 1 upon n1 whole thing square is strictly greater than 2. Note that since alpha is the least upper bound for t, alpha minus 1 upon n1 cannot be an upper bound for t. So this quantity is less than alpha, so it cannot be an upper bound for t. Therefore, there exists some t1 in t such that t1 is greater than alpha minus 1 upon n. Alright. So this is not an upper bound, means there is a t1 greater than this. That's what is written here. Now note that this quantity is a non-negative real number. Alpha minus 1 upon n1 is a non-negative real number. It cannot be negative. Why? Because alpha is greater than or equal to 1. By definition of capital T, 1 belongs to T because 1 square is less than 2. And alpha is an upper bound for T, so alpha is greater than or equal to 1. And n1 being a natural number is also greater than or equal to 1. So therefore, this quantity is always greater than or equal to 0. In fact, this quantity is positive. One can really check. Hence, it follows that t1 square is greater than alpha minus 1 upon n1 whole thing square, which is greater than 2. So t1 is greater than this, so this square is greater than this square, and this square is greater than 2. So t1 square is greater than 2, which is a contradiction because t1 is an element of t and every element of t has square less than 2. Thus it is impossible to have alpha square greater than 2. Earlier we have shown that it is not possible to have alpha square less than 2. Now we show that alpha square is not greater than 2 and hence alpha square must be equal to 2. So this completes the proof. It is not difficult to see that the above proof can be modified slightly to show that every non-negative real number has a square root in R. I leave it as an exercise for the viewers. If you like this video, then please subscribe and share my channel for more of such videos. Thank you.